Welcome to this presentation for our paper for the ICCCS 2015 IEEE conference held in Mauritius. The title of our paper is Full Half Duplex Mixed Strategy for Capacity Maximization in MIMO Interference Channels. This work has been conducted by Emmanuel Migabo, Thomas.olwal, and Thato, all from the Department of Electrical Engineering and French South African Institute of Technology at the Tshwane University of Technology in Pretoria, South Africa. Well, in terms of the presentation outline, I'll quickly give a brief introduction before I can present the problem statement and speak a bit about the related work related to our project. Then I'll present our proposed mixed strategy approach. After that, I will discuss the obtained results and give their interpretation. And finally, I will conclude and provide recommendations for future work. In terms of the introduction, as we all know, current ICT trend is toward what is known as IoTs, Internet of Things, where the idea is of connecting everything. However, that is associated with a certain cost, which, as far as we are concerned, consists of the increasing demand for higher data rates, which then triggers the quest for more and more spectral efficiency and creates the need to maximize the wireless channel capacity utilization. We all know that there are a couple of existing solutions to the problem. Channel capacity optimization is an old problem and has been attempted to be solved. The main existing solutions include K-Link's half duplex MIMO, K-Link's full duplex MIMO, as well as opportunistic communication, which includes things like cognitive radio. In terms of the problem statement, the existing purely full duplex MIMO has the advantage of using its spatial multiplexing capabilities in order to improve the channel capacity and to use its bidirectionality to double the channel capacity. This is because transmission and reception can happen on the same link at the same time. However, it also presents a couple of drawbacks, of which our research work has identified two main ones. The first one is the strong self-interference at the receiver front end. This is normal because if we are in a bidirectional type of communication, this implies that the transmit and the receive radio are on at the same time, and therefore there is usually a signal leakage from the transmitting antenna to the receiving antenna, and that creates what is known as self-interference. The other problem associated with this is that it's impossible to completely cancel the self-interference, and this is due to the electronics nature of the actual transmitters used on the field. These imperfections of the transceiver include the amplifier nonlinearity, the phase noise, the in-phase and quadrature channel imbalance. The second impairment associated with full duplex MIMOs is the inter-user interference. This is due to the fact that a node transmitting on a link I can interfere with another node transmitting on a link J, because we are talking about multiple links. The question here is, how best can we design the transmit and the receive filters with the available power? On the other hand, we also have purely half-duplex MIMO solutions. And these ones also suffer from they don't suffer from self-interference, but can only achieve, unfortunately, half channel capacity at a time, since they're half-duplex, meaning the transmit and the receive radio are never on at the same time. The global question is, how do we tap into the potential of both the full duplex MIMO and the half duplex MIMO while minimizing the impact of their drawbacks? Well, there have been some work conducted on this topic. most existing solutions include a purely half duplex or purely full duplex system. Focusing on the full duplex, purely full duplex MIMO wireless system as modeled by Ali Kagatai and referenced as 1 in the present presentation. The references, by the way, will be provided at the end of this presentation. But when we look at the figure on the left-hand side, it clearly depicts the scenario in the channel and models the different channels impairments. We consider K-links, as we can see from link 1 to link K. Since we've got 2 blocks, because each link consists of 2 nodes, then we have 2 K nodes. We assume that there are NI transmit antennas and MI receive antennas. Okay? They all suffer, of course, from the limited dynamic range, limited ADC and DAC resolutions, which create all the impossibility to fully cancel their self-interference. On top of the multiplicative impairments, which include interference, is an additive white Gaussian noise, okay, that is observed both at the transmit node, transmitting antenna, the transmitting node, as well as at the receiving node, okay, and is modeled as follows. As indicated on this slide, further details are provided in the paper. But as we move forward, we also realize that there's a parameter called phi ij, which actually, when given in terms of the square root of phi ij, denotes the channel's average attenuation between the transmitting node on the link I and the receiving node on link J, as derived from channel's average power gain, which is the phi ij. Another very important modeling parameter is the channel's gain between link K and between link M for communicating nodes A sitting on link K and communicating to a node B sitting on link M. We also have Ni1 and Ni2 to denote the distortion in terms of the additive white Gaussian noise signals at node 1 and node 2 on link I, respectively. From the channel impairment model, as described by Ali Kagatai in reference 1, a non-convex optimization problem has been formulated as a way or with the objective of maximizing channel capacity. It has been formulated as presented here, and as we can clearly see, the objective function is formulated in terms of weighted sum rate, weight, this is the maximum achievable rate, IIA by node A, so it's weighted sum rate. Weighted rate, sum. So it's weighted sum rate, WSR, okay? And this is subjected to the constraint of power, either of individual power or of total power. But in either case, it has also been proven in literature that it doesn't matter really the type of constraint one uses, either individual or total power, they both yield more or less the same result. Moving forward, this is for recalling, we all noted that full duplex provides double link capacity, but suffers from both self-interference and inter-user interference when sitting within a multiple links or MIMO system. Okay. And also, for proper operation of a MIMO system, being subjected to self-interference in the full duplex mode requires then a certain minimum self-interference cancellation happening at the transmitter level. And this is according to reference 6, which is provided by De Hengerhardt and Klein. In terms of the half duplex, there's no self-interference. This is due to the temporal multiplexing of nature of the half duplex. But there is half capacity, that's the disadvantage. The multiple link come with the inter-user interference, which is therefore the only multiplicative impairment happening in half duplex. And the additive one, of course, is always there, the noise. Distortion at the transmitter, distortion at the receiver. In general, it has been proven through literature that half duplex MIMO channel capacity is usually or often less than full duplex MIMO capacity. And this is according to Shin and Moon as provided in reference 13. It has also been proven that increasing transmission power improves links capacity in both half duplex and full duplex. But it also has a negative impact when it comes to full duplex because it not only it increases or improves the link capacity, but also increases its self-interference, which is a negative aspect. In terms of radio devices imperfections, they cause impossible total interference cancellation. Therefore, since we cannot get a perfect cancellation of the self-interference itself, we need to optimize and get the best possible results. Now, which solution do we propose to solve the problem? Myself and my two colleagues decided to propose a mixed interleaved half duplex and full duplex K-links approach with the objective to enhance channel capacity performance. But how? By achieving double link capacity while maximizing capacity and at the same time minimizing inter-user interference. That comes with the interleaving. As we can see in the figure to the left-hand side, as I'm pointing to it, we interleave full duplex links with half duplex links. The idea is basically the same. Get advantage of the full duplex links in terms of double link capacity and reduce self-interference by using half duplex interleaved between full duplex links. Okay. As we move forward, the additive wide Gaussian noise distortion at the transmitter and the receiver can be modeled, of course, as a random variable and has been found after some work conducted by us to be modeled with the following covariance matrices that we name CIA and EIA and provided by the two equations, the two following equations. As we can see, it has a normal distribution, zero mean, as well as a variance which depends on the transmit filter and its conjugate transpose. Same goes for the receive AWGN distortion. The idea is to design then the optimal transmit and receive filters for both half duplex and full duplex. And this assumes that we have knowledge of the desired or received output signal. The desired received signals are the signals without self-interference, for instance. This is the signal with self-interference cancelled and is modeled as Y with a small cap, being the actual signal being received minus the impairment. When it comes to self-interference, it's normally known at the transmitter and therefore can be taken care of in a deterministic way through the design of an optimal transmit filter that will get rid of it. But when it comes to AWGN, as well as, of course, AWGN transmit and receive distortions, as well as the inter-user interference, this is very unpredictable and very non-deterministic in terms of its nature. It's stochastic in nature, random, and therefore very often difficult to take care of completely. But what we do normally is to minimize it. So it is being modeled as ZFDIA for the full duplex links and ZHDIA for the half duplex links. Based on the model as further described in the paper and shortly described in this presentation, the following optimization problem has been formulated. First of all, in terms of the weighted summary. This time our links are mixed. We've got full duplex and half duplex, and the variable therefore is a mixture of both full duplex transmit filter metrics and half duplex transmit filter matrices. Okay, and the constraint remain in terms of individual power or total power. Both are acceptable. However, the formulated problem has been found to be non-convex, and due to its non-convexity, it is difficult to solve. Therefore, we proposed a change of variable from the weighted sum rate maximization problem to a weighted minimum mean square error minimization problem, because this one is no longer, it's actually convex now. And the fact that it's convex, it will be easier to solve than the WSR, which is non-convex, and therefore difficult to solve. How do we solve the problem? That's the next question. In terms of the optimization solution method, we chose to use the Rosen's gradient projection algorithm for a couple of reasons, of which the main one is the fact that it's an iterative method, and we expecting to also, at the same time as we test the channel capacity performance, try to see how fast the method converges in terms of future expected implementation on real DSPs. Okay. And the objective function to be therefore optimized is defined as following. When it comes to simulation parameters setups, we decided to use 800 bytes in terms of the transmission data stream size. Up to 5 MIMO links, good enough. And with 2, then 3, then 4 number of transmitters and receivers per node. The idea of having 2, 3, 4 number of transmitters and receivers per node was to test the impact of changing, or to be specific, of increasing the number of transmission and reception antennas on the overall channel capacity performance. We also have the receiver and transmitter distortion parameter gamma, given by minus 40 dB, and we are using a positive WSR weight coefficient mu of 1. In terms of the step length optimization, since this is an iterative method and therefore requires an optimum step length at each level to fast the process, we are using the famous dichotomous optimization technique. After simulating, computing the solution of the optimization problem, formulated optimization problem, using the proposed optimization solution technique, which is, as presented here, it is the Rosen's gradient projection algorithm. The following results were obtained. On the left-hand side, what we refer to as figure A, it shows that at low power, the full duplex has got better spectral efficiency than the mixed strategy, but as power slightly increases above minus 3 dB, half watt, sorry, the mixed strategy provides better spectral efficiency than the full duplex. As power keeps on being increased, the capacity of both full duplex and mixed strategy seem to converge toward the same value of 100 bits per second per hertz. This is acceptable and makes sense because power cannot indefinitely keep on being increased, and therefore has got some sort of saturation. It is the limiting power. That's why it describes the constraint in terms of the optimization problem. Looking at figure B, the solution to the mixed strategy problem by Rosen's gradient projection converges slightly fast compared to the one of the full duplex problem. And as we move, we see that also in the same figure, from iteration 6, more or less, well, the Rosen's gradient projection algorithm for both the full duplex and the mixed strategy remain quite steady, meaning it takes at least 6 iterations to more or less achieve the optimum possible results, which proves sufficiently that the gradient Rosen's algorithm method or method is quite suitable for solving this type of problem. 6 iterations is not a lot. When we look at the result in figure C, they show that as power is increased, the spectral efficiency also increases as the number of transmitters and receivers antennas increases. This has a considerable impact on the sum rate or channel capacity, spectral efficiency. As we can see, it literally doubles for 40 dB signal to noise ratio from 100 bit per second per hertz to 200 bit per second per hertz as we move from 2x2 type of full duplex mixed half duplex mixed strategy MIMO type of setup to 4x4 mixed FD-HD MIMO. So there is a gain associated with increasing the number of antennas. But we recall as well that we cannot indefinitely increase the number of antennas, as this is also subjected to the available amount of power, which therefore constitutes a constraint. In terms of conclusion and future work, we will note that the mixed strategy, full duplex and half duplex capacity performance has been investigated throughout this work. Tedious channel impairment modeling in terms of inter-user interference as well as transmit and receive distortion impacts has been modeled. The weighted sum rate maximization problem has been formulated and found to be non-convex, therefore converted to a weighted minimum mean square error minimization problem, which is much easier to solve. In general, channel capacity and solution convergence results reveal that the mixed strategy outperforms the full duplex channel optimization method. The impact and limitation of the increased number of transmit and receive antennas has revealed that the mixed strategy being used and the number of antennas being increased result in the improvement of channel capacity performance. As future work, it will be interesting to apply the mixed strategy to the cellular system scenario with additional parameter that comes into play here, which is therefore the co-channel interference that should be now considered between the different users sitting under the same cell and being served by the same base station. Studying that impact or that application of this mixed strategy in a cell-based context will be our future work. These are the different references we went through, and thank you. For further information, do not hesitate to contact me, Emmanuel Migabo, on the address migabo.emmanuel@gmail.com. Thank you.